Sorry about that. Did we all get kicked?
Looks like it.
Okay, I guess I feel better that it wasn't just me.
It dies. Everybody just died. Yeah.
Yeah, let's give it a minute or two and let people get back in.
Sure thing.
What did?
Guess who died today?
An actor?
Well,
Singer.
that was unexpected.
Boy or girl?
Girl.
Diana Ross.
Christine McVie.
Really? Chris McPhee's Fleetwood Mac. Oh.
So it was their system, not your
I think
computer.
everybody's going to have to mute their own microphones.
Okay.
Yeah, that was weird. Sorry about that, folks.
Thought it was the end of the world or something.
I don't know if you can mute everyone, Everett, because I think everybody's microphone came back hot.
See,
Yeah, let me try the.
you use 3 tablespoons. So you use a half a cup of.
She was at a hospital. And the company never.
Let's see.
I was able to mute somebody, so.
Back in, we didn't lose the chat session, so the chat session's still active. Didn't do a restart, at least. Recordings probably need to be restarted.
Actually, it's going, but it shows 1:44, so that might have been what bombed us out of there. The fact that I couldn't turn off the recording, but let's see. Do we have our speaker back?
Yeah, I'm here.
Okay. Why don't you go ahead and take it away, and we'll just pick up right where we left off. And I apologize for that, but technology.
Okay, yeah, sorry about that. Hopefully I didn't crash the whole system down, but that was exciting.
No, I think I know what happened there.
Okay, all right, yeah, I can go ahead and move forward. I think we were just talking about the elevation difference filtering. I was just wanting to point out that the scatter map there in the bottom right shows how that's applied, where we have our fire represented by the star and our 3 profiles represented by the circles in our radius. The ones on the east side of the fire remain after the filtering because the elevation is quite similar. And then you can see that in the valley and the lower elevations where you would probably get some profiles, those have been filtered out. And we end up averaging about 6 to 7 profiles per event. And then I do want to point out, if you click the arrow maybe once or twice, it should highlight the box here, which is that we're using these model inputs. We're using CAPE, SIN, vapor pressure deficit, LCL height, lapse rate, and in the mid-troposphere, we're looking at potential instability of precipitable water. Specifically, we're looking at the most unstable parcel, which would more closely represent the conditions near a hot fire. Next slide, please. So for our null cases, we're defining this as a case where an intense wildfire event did not produce a PyroCB. I'll remind you of the yes case filtering here. The spatial distribution that's the result of after the filtering is shown in the center bottom image. That's the distribution of our cases where we have them ranging across Western North America. We've got one in Alaska. In 2021, we had an outbreak in central Canada. And then for the null cases, we consider the same filtering techniques, but we also want to consider the intensity of the fire. So we want to get high intensity fires that didn't produce an event. So we consider fire radiated power, fire pixels, and then we also make sure that we're not pulling in any profiles within close proximity, whether it's time or space, to a known PyroCB event. And the resulting distribution there is quite similar to what we have for our yes cases. Next slide. So this is just a bunch of lines. This is the result once we've compiled all of our training data. The top row is piracy B events, and then the bottom row is our null cases. And I have separated these out according to elevation because that does have an influence on things, and that'll be a theme over the next few slides. We have in the top row, we have our SKUTs, and each line on the SKUT is an average profile for the event. The solid line is the average of all of them, and then the dotted lines are the standard deviations. And I just want to point out that there's what we call an inverted V at the bottom for the low and mid elevations, especially of these profiles where you have dry conditions near the surface, moving towards moist and unstable conditions in the mid-troposphere. And we do not see that type of signal from the null cases where the spread is much greater. We don't see this inverted V. The standard deviations are much wider. And that's what we would expect to see. So that's good news. Next slide, please. We'll begin with the lower troposphere. Plume-dominated behavior is an essential first ingredient here. So steeper lapse rates and larger vapor pressure deficits have been associated with piracy B events, especially at the higher elevation fires. So I've gone ahead and circled those for you to see. So at the mid and high elevation categories, and we've separated them out into yes and no cases in these box plots here. So the left side is showing vapor pressure deficit, and you can see that we have larger vapor pressure deficit for the yes cases relative to the no cases. We also have steeper lapse rates on the right side for the yes cases relative to the no cases. And if you hit the arrow one time, we can compare that with the known climatology. So again, that's from the Peterson et al. In 2017 paper, where they show that the lapse rates are steeper for piracy B events than for cases where it didn't happen. Next slide. We can see similar trends for the mid-troposphere. So in the mid-troposphere, coincidence of moisture and instability are essential for piracy B development, and we especially see more separability in the distributions for piracy B events and null cases across each elevation category. So we have precipitable water here and potential instability on the right. We can see that we have higher moisture for the yes cases relative to the no, and more instability indicated by lower values on the right side for the yes cases relative to the no. If you hit the arrow, we can compare again. So we can compare precipitable water to the known climatology, very similar, both between the yes and no cases, but also the trend across the elevations. Hit the arrow once again. And for potential instability, we see the same kind of pattern. So this is also very good news for the use of these values inside our model. Next slide, please. So we put all this into a logistic regression prediction algorithm. Just to remind you, we're using 2020 through 2021. It's pretty simple. We just label the events as 1 and the null cases as 0. The column inputs we use are CAPE, SIN, vapor pressure deficit, LCL height, lapse rate, the mid-tropospheric potential instability, and precipitable water. We randomly select 75% of the data to use for training and 25% for testing. And the result is what you get on the left. I'll focus on the confusion matrix there. In the top left, we call those correct negatives, where the model predicted no case or no event, and there was no event observed. In the bottom left, we have our misses, where the model did not predict an event, but an event was observed. In the top right, we have false alarms, where the model predicted an event, but no event was observed. And in the bottom right, we have our hits, where it correctly predicted an event. And so the good news is that the big values are in the top left and bottom right. And the raw numbers are in the top left, where you can see that we have accuracy near 75%, probability of detection is high, false alarm rate is low, and the Heidke skill score indicates that this model has skill beyond just random forecast. So these are good preliminary results for our first run here. Next slide, please. But we don't want just a yes or no prediction. We want probabilities. That's the ultimate goal. So if you just hit the arrow once, the model is outputting probabilities. And if we overlay them for each of our cases here, I've added some lines for some context at 25% probability, where you can see that the model predicted higher probabilities for misses than for correct negatives. A larger density of the probabilities are in that higher than 25% case for misses than for correct negatives. So that indicates that the model is more certain for the correct negatives when it gets it right than for misses where it's predicting closer to 50%. Hit it one more time. This is the same for the false alarms and the hits. If we draw the line at 75%, we can see that for the hits, the model was much more certain, had a greater density of probabilities predicted above 75% compared to the false alarms. And so again, this is good news for us using our probabilities in our prediction algorithm moving forward. Next slide. Our ultimate goal is to produce a product that's similar to those produced by NOAA. Examples of these would be on the SPC mesoscale analysis page. If you're not familiar with that page, I highly encourage you to go visit it. They have quite a number of different statistics and parameters that you're able to look at. We're hoping to get something similar to what they have on there. Our next steps would be to refine the logistic regression model, so to see how different inputs change the output and how limiting things to certain elevations may change, things like that. And then we'd like to perform an independent test using the 2022 fire season. We do have a satellite data processing system already at NRL, so we just need to implement the NUCAPs algorithm within that. And then we can begin real-time processing of NUCAPs data and hopefully real-time testing for the 2023 fire season. And I think that's all I have. I'm sorry, I think my email's cut off at the bottom there, but happy to give that to you if anyone wants it. And field any questions.
I'll make sure that gets shared. I don't see anything in the chat, and I apologize for getting hung up in the middle of your presentation there, but I think we need to move on to the next presentation in the interest of time. And Joaquin, there you are. You're going to share your screen, and I'm going to unshare mine. So when you're ready, go ahead, and I'll come back on with my camera when you have about 2 minutes left.
Thank you, Everett. Can you hear me okay? Can you see my screen?
Yes. Oh, well, I can see you, but I don't see your screen just yet.
Let's see the screen. How about now?
Yes.
All right, excellent. So thanks to the team for just getting us together a couple of times a year, at least. It's really, encouraging to see all the efforts on this topic. My name is Joaquin Ramirez. I run a company called TecnoSilva, and we are basically doing wildfire technology for many years, actually 25 years now, and just been really exciting to see all the evolutions. And we've been fortunate to work with many of the agencies that are present here. I'm gonna introduce today a new index that we have created after the experience that we had in the last 4 years working in California with CAL FIRE closely and with the utilities. And that we expect is going to be, filling a gap of the actual predictive danger system that we have out there. It's called the Extended Attack Assessment Index, and here it comes. The motivation to develop this index came after some discussions after the last two, as you know, 2020, 2021 were really terrible fire seasons. Fortunately, 2022 gave us a little breath. And there's been a process and a ton of conversation about what could be the capabilities for providing a more granular and a better intel to the intel units, both whether it's a gag levels or a unit level or even an incident level, that could involve the actual significant fire potential index that is created from the National Wildfire Coordination Group, and is run at the gag level and defined at the different pre-incident services areas. This index, these metrics have two objectives, and the objectives of the question that they're trying to answer is what we try to say, okay, can we do it better with the new science, with the new data? Can we extend and evolve the solid work that is being done through the different predictive services? And that's where we can, that's the motivation. The two questions are, okay, what is the daily probability for a new large fire occurrence, and what is the potential for significant new growth on an existing large fire? Those are the two two answers that the predicted services want to support with these indexes. So that was the motivation, and what we came with the standard attack assessment index. The standard attacks is a danger index. It's not a risk index. We're not running simulations on this one. It's an index that is being evaluates the potential of fire activity, and it's a machine learning index that is validated with remote sensing data. Actually, we build it on top of the BIRS hotspot database. This index is providing a 3 hours update for 7 days based on new metrics that expanded net DRS with some variables that are not available before. And actually, I'm really glad that the past presenter talk about the convective fire behavior. That's one of the things that we take into consideration, that they are not captured with the previous models that we used to talk about, whether it's the surface spread models or the danger models. The resolution is about 1.75 miles for every one of those 50 sign time steps, covering the whole Western US, and it's about 600 million, 0.6 billion of data points. And it's provided, it's integrated into our wildfire analysis product line. Just a diagram to see the differences between the actual fire potential model from predictive services. We are included some variables, as we mentioned, that are a little different, are evolving actually, some of them, because we are working with Matt Jolie to try to integrate some of the NDRS, like for example, the ERC or the field moisture 1000 hours, or the severe fire danger index inside. But as you can see, we include information about the fuels, information about we call it fuel complexity, because we're taking into account not only the type of fuel, but also the fuel age, the amount of biomass, and the potential affectation by pest. Where the fuel's availability with a well-known vapor pressure deficit, the terrain difficulty for suppression activities, taking into consideration the draw, and evaluated different configurations of ADDI. We go with EDS is one is the best one. One for another variable to evaluate the instability, the well-known lifted index in connection with lighting data, and also we call it the potential for convection. It's an index that is derived from the Paracumulus fire threats power potential index that from Kevin Torrey. We made an adaptation to make it actually, that's been led by Scott Purdy, our lead meteorologist, fire meteorologist. And it's called convective flap. But basically, it tries to identify those situations that were described before. With all of that, it's done every 3 hours, 56 time steps. That resolution. It doesn't include the extremely valuable spread analysis. It doesn't. This index is just going to be another toolbox, another tool in the toolbox for the predictive services or the intel units on fires. I would say that this extended attack index, it's a part of it's the extension of an initial attack assessment index that we have been delivering for the since 2019 for inside wildfire analysis for Cal Fire and the Western US, and major utilities are using it operationally. Basically, every individual alert is addressed with the likelihood that it can escape from initial attack. So here on the left, you can see that every initial alert that appeared during, for example, this is the firestorm that we had in Labor Day weekend in 2020. All of the fires are evaluated 1 to 5 with a series of, these ones are based on simulations. And all of them are in 8-hour simulations that compute as risk index because it's computing also impacts. And that is every individual simulation we've gone through a thorough evaluation process. Actually, we're just presented in the conference the validation of all these operational fire threat models in California. We went through close to 2,000 individual fires tracked through the FireGuard product, which for us, it's an absolutely, as Tim Chavez was saying yesterday, a game changer product for us. It really helped us to not only validate, but improve the operational wildfire models. And that was presented in Coimbra. And also with this same simulation, we're running about 500 million simulations every day, covering the Western US every 3 hours to compute that initial attack assessment index. The standard attack is a danger. Again, it's not going through simulations. and it's getting the data from different sources. It's coming from here, like fields coming from Tecnosilva and fire perimeters, and obviously the super our ground validation, our proxy for fire activity, which is the BEERS dataset that from 2012 we've evaluated. That's really a very good proxy for fire activity. Just go through some partial dependence plots very quickly, but just to give an example, basically we're trying to get through the machine learning analysis applied to these data sets, and obviously to define the variables. We went first through a expert review with the suggestions from the CAL FIRE team, Jeff Marshall, Tim Chavez. I mean, what is what the events are looking when they know that there is fire on the ground. They already have fire there. They don't care about the initial simulation. They want to know which are the windows of opportunity. And we came with those variables, and the model selected the ones that I just presented. But this is an example of how it is validated. In this case, we have the dependence plot between the terrain difficulty index. The most complex is the terrain, and the combination with the fields and terrain, lighter colors indicate higher complexity. This is the explanatory variable. In this case, is the BEERS, the predicted BEERS activity that we have the model. And in any of the models and any of the variables are evaluated for the contribution in the model in a similar way like this. So we deliver all these variables daily, operational in Western US inside Wolf Analysis. It's right now on one utility, and CAL FIRE is going to start to evaluate it during this 2023 fire season. It's done at a scalable, it's based on a scalable framework called H3, so we can work at different resolutions with different data. And I'm gonna go just demonstrate some examples, because what we're going is to running the model. We build the model, we evaluate it with the BEERS dataset, and then we run the model, and we have 3 years of every 3 hours calculations of the model. And I'm gonna go through some examples. In this case, for example, we have the North Complex Fire 2020. We have all the model was indicated that we're on the string category until we have the 8th. In this case, it was derived because we provide all the individual data for the specialists, so they can identify if this is due through wind or VPD conditions or through convective conditions. Again, we also have the creek fire. We have all the evolution of the creek fire. It was absolutely also captured both on the 6th and on the 7th. Here, what we see on top of the index is the BEERS datasets for that period of time. So we are comparing both activities. Lighting complex. Here we see 3 variables. Here we see the lighting event that we have in 2020 that started all the firestorm. We have all the Western conditions like this. DIA was marking in all this area that started on the extreme or very high conditions. If we look at, for example, the convective flag, we have some areas that were providing the capability, the chance to having a convective fire behavior, and also the lifted index that was given the information about the potential unstable conditions for development of thunderstorms, etc. Dixie Fire, that's the day that we have the biggest growth, where we have the fire is marking also on the very high extreme conditions, but we have the convective flag also into moderate to high conditions that were the one that would drive all the paracumulus activity. So what we tried is validate, again, for us it's extremely important that when we provide information to the users, this is, for example, the Calf Canyon, also the same activity, same marking of the activity, all the area was marked on the same neighborhood in April. For us, it's extremely important that we validate the tools that we're providing to our inter-community with real data on the actual fire behavior. This year, for example, we have the McKinney, the values were really high. Then all of a sudden it went into the purple. Then we have all the convective activity, kept the next day, and we knew with 3 days in advance, actually, since we started to look at the fire, we knew that everything was going to be dropped on the 1st of August, and actually it was like that. Really, really, really very solid and very operational validation. The same with the mosquito fire, same with the Fairview fire. Then activity, and then it dropped. So the level that we are providing this tool is, we think that is a very appropriate to understand when there are windows of opportunity when you already have a fire on the ground. These are some examples of different fire activities in the West. It provides the granularity of giving 8 timestamps during the day. It's not only one for the whole day. It's granular enough also to make and summarize the information at the different administrative level. For example, you want to know your index for your national forest, for your national park, or for your unit, or for your dispatching area, or for your weather zone. The way that we structure the data can allow to summarize the data in that way. We also obviously want to improve the model with better resolution. We're working on including the calculations for the. Right now, we're using the national blend for the calculations of the convective flag activities. We want to go at the level of the WRF model that we are providing to CAL FIRE, and the utilities is based on 2-kilometer resolution, 124 hours. We want to extend it and use that data. I want to also collaborate with Dr. Tim Brown from the CANSAC to utilize his CANSAC model at 1.3 kilometers. We're really excited about that. And as I mentioned, to integrate the SDI and DRC and some of the metrics on the FDRS to really make a smooth transition and and connect with the actual NFDRS data. And I think that's as I mentioned here, we have a screenshot already in the Wolfram analyst, and I think with this, I hit my time.
Well, thank you, Joaquin. Let's see, Dave Jones, in your opinion, what would it take to put together a prediction by acre of fire behavior? Also, what pathways will the fire take to spread based on fuels? This is the emerging requirements request from firefighters. Thanks.
Well, that's already, that's a good question, David, but that's already out there. I mean, that's what we're providing for CAL FIRE. We've evaluated more than, I think it's about, CAL FIRE analysis has evaluated more than 70,000 simulations of more than 30,000 individual fires constantly. That's the Firecast fire scene. I haven't talked anything about that, but I think that we presented something in the past. But that's been operational. Well, not only CAL FIRE, actually, we have it, worldwide. We're working in Chile, we're working in Canada, we're working in Europe. That's something that Wolfram Analysis provides, and it's, and as I mentioned, try to prove the usefulness during operations with the publications that I just mentioned. So yeah.
Okay, well, thank you, Joaquin. That was great. Really interesting work that you're doing there, and I think that that's really going to help on the operational front. We'll go ahead and move to our next set of speakers. We actually have 2 that are part of the water drop challenge. And do we have, let's see, I think our first one is Colin Fisher. I saw Colin on earlier.
Hi there, can you see us?
Yes, I can. And I gave you 20 minutes because I noticed you had a lot of slides, but if you could keep to 20 minutes, that'd be great. I'll turn my camera off, and then about 18 minutes, I'll come back on again. And then we'll do the second one. Yours is the team H2 Aero, and you're from Virginia Tech.
Yep, that's us.
Okay, well, go ahead, and I'm going to go ahead and turn my camera off and take it away.
Are we sharing screen, or are you sharing screen? Sorry.
Oh, I am sharing screen. Thank you for reminding me to turn that back on again. I thought I had. There we go.
Perfect. Awesome. Well, hi, everyone. Thank you for having us today. We're Team H2 Aero. We're a group of 9 undergrad students from Virginia Tech who participated in NASA ARMD's University Challenge. Our team designed an aerial firefighting vehicle that is based off of some of the design trends seen in the urban air mobility and regional air mobility design space. Next slide. So again, my name is Colin Fisher. I was the team lead and project manager for this project.
I'm Kevin Carey. I was the deliverables manager. I also worked on the propulsion system design.
We had a couple other students who couldn't join us today, who were also subject matter experts for this project and were very influential in driving this design. Next slide. So this is an overview of our water ram design. Our water ram is a fleet of 4 vehicles, as pictured in this slide. Water ram is actually an acronym for water acquisition and targeted release, regional air mobility. Next slide. As I don't think I need to really talk about the problem genesis too much. Usually we'd do this presentation to some of our faculty advisors, but I will go ahead and say that one of the key design drivers for this project was that we were looking at the current fleet of vehicles being used for aerial firefighting purposes. And really what we saw is kind of a division along 2 lines. One, you have these very large air tankers that have been retrofitted for the purpose of aerial firefighting that have great range and payload capacity, but had trouble with accessing water close to the fire site, needing specialized equipment for reloading the water tanks, as well as rotorcraft, which had the ability to access fires more locally, but of course had payload challenges. So with the urban air mobility and regional air mobility vehicle market, we saw a capability to introduce a vehicle that could acquire water at the fire site through a very short takeoff and landing instead of a vertical takeoff and landing, and then deliver that water to the fire lines, and thus perhaps increasing the total amount of water that could be delivered over a 24-hour period. Next slide. So our system design, I'm just going to go over some of the key aspects, key design decisions that we had for this vehicle. Next slide. Our water ram is each individual vehicle has a total takeoff gross weight of about 19,000 pounds, which puts it in the potentially in the Part 23 requirements of the for the FAA, allowing us to use this vehicle outside of the scope of just aerial firefighting, but also for sort of a regional transport vehicle. It has a cruise range of about 1,400 nautical miles and an operational radius of about 360 nautical miles. We'll talk about that a little bit in our ConUps, as well as a 750-gallon tank in each vehicle. For our proposed fleet of 4 vehicles, this would allow us to drop 3,000 gallons of water per drop per approach to the fire. Next slide. So in investigating, I guess this design that we came up with, we had a lot of decisions we had to make. One of the key decisions was whether we would go with a piloted system versus a remotely piloted system. There has been a bit of a trend in urban air and regional mobility to move towards either remotely piloted or optionally piloted vehicles. We think the single piloted vehicle would be best for the use case of aerial firefighting, just because a lot of the operations have to be done close to in a low altitude environment where quick decision making is needed. Plus, having a human in the loop who can make quick decisions and kind of the versatile mission operations was very important to us. Next slide. Additionally, we had a team member who was very good with ensuring that we had suitable control at the slow speeds that are required for the water drop segment. Thus, we decided to go with an H-tail, which we think will give us very good control during the water drop segment, as well as a high lift airfoil, which Kevin will talk about a little more, which works in conjunction with our distributed electric propulsion system. Next slide.
Yeah, to go into our water acquisition and scoop tube system, we ultimately had a system that was designed to, because it's a fixed wing aircraft, it's not stopping in a situation analogous to helicopters where they're able to float over or hover over the water. So we have a tube that is going to stick out the bottom of the aircraft. This was seen in some other more recent aircraft designs, and it will suck up into this 750-gallon water tank with a mechanical hoist. Next slide. We also want to touch upon that one, modularity. We want to touch upon the regional air mobility part of this aircraft. One large issue in terms of designing aircraft like this for firefighting aircraft is for a company to be able to produce these at scale and for it to be economically viable, they need to reach as large of a market share as possible. So we want our aircraft to be not only viable for firefighting design, but also for other things. And we're targeting the regional air mobility market, allowing us to carry passengers from little used aircraft sites throughout the United States. Next slide. Then to touch upon our propulsion system, to contextualize this aircraft's design, the problem was targeting an entry of service of about 2030. So taking into consideration some of the evolving technologies with a lot of electric aircraft, as well as the battery capacity and density, we looked at a system that was novel compared to some of the older firefighting aircraft, and that we're going to have a hybrid electric system that allows us to incorporate a distributed electric propulsion system along the wings that have these very small propellers that have the effect of not only generating lift during takeoff, but thrust at the same time, which allows the aircraft to take off in a shorter distance compared to a traditional setup. Next slide. All right, now we're going to talk a little bit about our proposed solution, as well as some of the philosophies our team went into with designing this aircraft and the initial design behind it. Next slide. Okay, I'll just go over this really quickly. The NASA RFP document outlines some of the design requirements which we needed to target with our aircraft. Most notably being our suite of vehicles needs to be able to deliver 3,000 gallons of water to a fire location in a single pass. So with our aircraft's design, or our fleet's design, we have 4 750-gallon drops on target. There's other things outlined here as well. We just go into the next slide. Our team ended up generating some measures of merit to measure our aircraft's effectiveness against the RFP and NASA's stipulations for our design. All of these are important, but we really wanted to focus on the top 3, including delivery volume. Obviously, if it's firefighting aircraft, the more water we're dropping on the target, the better it's going to be. We also really wanted to stress that water availability to address that gap we noticed with Forest Service aircraft, either being those large tankers, which carry a lot of water but are very inflexible in what bodies of water they're able to refuel from, as well as helicopters, which can refuel from a lot of locations, but they can't go very far, can't carry too much water, things like that. Next slide. Key design drivers, we really wanted to focus on that very short takeoff and landing performance, not VTOL. We'll go into this a bit later. We did an analysis on fire locations and lake locations using GIS, global data from a geography site, to really quantify the utility we're getting out of having an aircraft with VTOL versus VTOL performance. We ultimately decided the benefit we're getting out of a VTOL aircraft and being able to have very much flexibility was not worth the trade-off we would have. Next slide. All right, yeah, now we can go into a little bit with this wire fire simulation. From what little we've seen, we can tell there is very much quite a rabbit hole in terms of simulating and predicting wildfire locations as well as their growth. So you can imagine this was from the context of a college group and just trying to answer a problem. But we can see like the research being put into this can really be substituted for this kind of thing, and it shows directly how that research can be used to help design aircraft to be better suited for targeting fires like this. What we ultimately went with is we made randomly sampled fire locations using a Monte Carlo simulation across the borders of California, and we cross-correlated that with lake locations in California as well as their sizes. as like larger lakes would be able to have a larger takeoff and landing distance, larger acquisition distance. They're more flexible to be used. And we ultimately ended up generating a curve that allowed us to quantify the benefit we're getting out of an aircraft with a smaller takeoff distance in terms of how far does that aircraft have to fly the fire in order to drop water on it. Next slide.
I'll talk briefly about our proposed concept of operations. This will probably be difficult to do if I can't control the slides. So if you could just go to, just skip a couple of times through the animation until basically everything appears in one. Perfect. All right. So this is kind of our concept of operations that we came up with that drove our, I guess, conceptualization of this design. Since our aircraft is a hybrid electric power plant, we can still refuel our aircraft at the field. We don't need to wait for the batteries to charge in order to take off. Really, our propulsion system is there only for the takeoff and landing segments, as well as during water acquisition, allowing us to cut that balance field length down quite a bit without really hurting our range. Once our aircraft have taken off, they will actually they will cruise without their water tanks full to the closest water collection site, such as a lake, river, or stream close to the fire location. Deploy that scoop tube we talked about earlier to acquire the water. Then establish communications with ground crews if possible, and coordinate the water drop at the location. They'll continue to circle back to the nearest water location to scoop up more water, and thus providing more time on target to increase the water dropped over a period of time. After basically our range is no longer viable to do another drop, it'll return to the airport where it can quickly refuel and get back to serving this mission. Next slide. Of course, one of the most important things to consider when designing an aircraft are its competitors. If the aircraft does not provide any additional benefit to its competitors, or it doesn't have, or if it's too expensive, of course, it's not going to take off. We chose to compare our aircraft to the very popular Super Scooper, as well as the CH-46 for application for aerial firefighting. Of course, both these aircraft are extremely capable and good at what they do. However, we saw that our aircraft, the water ram, could provide more water on target, or could provide a larger water drop, which is the 3,000 gallons that the RFP required, as well as reduce crew requirements, which inherently will reduce the cost of the aircraft. Next slide. Additionally, a lot of the technologies that we are considering for this aircraft, we did some research into to make sure that they would be viable solutions for our entry into service of 2030. Namely, the water scoop tube. We did a lot of research into it to see if this would be something that was viable and safe, as well as the synthetic vision system that we proposed for our pilot to increase the safety of the operations. And the distributed hybrid electric propulsion system that Kevin was talking about earlier. Next slide. So we'll go into our design evolution next and talk about some of our initial concepts and basically how we arrived at the concept that we're presenting today.
Yep. So ultimately, we had 8 people on our team. We all were tasked with coming up with an initial design based off of what we thought was appropriate for our aircraft, seen at the top there. One is missing. Ultimately, we moved forward with merging some of the best aspects with the initial designs we had come up with. And we ended up with an initial design seen on the bottom left there. One key component with that aircraft that was different from our final design is we had partial tilt rotors involved, as we really wanted to stress and nail down getting as low of a takeoff distance as possible to maximize that flexibility of our aircraft being able to gather from as many water sources as possible. However, in the end, we ultimately decided against having this tilt rotor functionality as the mechanics involved with causing the aircraft to be able to move its props and rotate them is ultimately not worth the extra weight and cost associated with the additional complexity with that component. Next slide. To talk a little bit about our water acquisition a little bit more, our final acquisition distance came out to be about 900 feet from our calculations, which means we're able to target lakes with a valid stretch of water about 900 feet or so. Using that scoop tube we mentioned earlier, the aircrafts, we did some research into the baffle design in order to optimize for water slosh as well as CG travel along the wing due to dropping water and water being sloshing around at the tank to make sure we're not having any stability issues during flight after we drop the water or after we pick it up. Next slide. The water dispersion system here, we can talk a bit about this. This was covered mainly by Salon, who's not present here on the team, so he knew more about it, but to go into detail, we ultimately had some avionics systems that were allowed to use some more modern technologies to allow us to do automatic wind correction when dropping the water on a target site to allow for more accuracy and to make sure we're not missing the fire or dropping it in inefficient locations. Next slide. Yep, to go over the propulsion performance a little bit more, I see we're running a little behind on time because we have a lot of slides. This ultimately was a pretty long project, so I'll try and go through things quickly. We ultimately had a system, as I said earlier in the presentation, that was a distributed electric propulsion aircraft due to emerging technologies coming up in about the next decade or so, allowing for increased viability of electric or hybrid electric aircraft. Our system here uses two twin turboshaft engines hook up to electric generators that operate in tandem with an auxiliary battery pack to provide a DC power to both two wingtip propellers as well as a distributed electric propulsion system that is active during takeoff to allow for enhanced and shortened takeoff performance. Next slide. To go a little bit more into the electric propulsion components, there really is a lot of uncertainty with the technological improvement with these, as it is hard to accurately forecast how these components are going to be performance-wise in about 10, 20 years from now or so. But ultimately what we are seeing is a lot of companies are really making great strides in improving the power density of these components that is making it really more viable to look into these for future aircraft designs. Next slide. Touch on that.
Yeah, sure. I'll touch briefly on the aircraft manufacturing side of things, and after that, I think we'll be finished. But one of the key things that we wanted to enable with this project is have an aircraft that could be fulfilling both multiple uses for the Forest Service, as well as being able to convert to a regional air mobility vehicle that could be used for air transport of various means. So to enable this, we're very much focused on having an aircraft that had a high part similarity between our aerial firefighting version and a regional air mobility version. And we wanted to approach the manufacturer that's similar to the Cessna Caravan assembly line has accomplished. One of our the cost manufacturing leads was very involved with this and was able to ensure that our aircraft costs could be brought down by ensuring this part similarity. Next slide. So I think we're done at this point. Thank you for your time. Appreciate it very much. I know we haven't covered this. We finished this project back in May, and I wish we had our whole team here to kind of discuss each of the individual parts that we got to work on more in depth. But thank you for your time.
Thank you, gentlemen. That was good. I also meant to mention Liz Ward, who I believe is online, who brought your work to my attention in the first place from NASA. So I guess in the interest of time, we'll go ahead and switch to the next team, which is Jack Barland. And I don't know who else is with Jack today, but I need to switch to presentations here, so this will take me just a second. if Jack would like to come on, do a sound check. And I'll stop sharing for just a second here. And bring up the other presentation.
Can you guys hear me? Am I good?
You're good, yeah. If you want to get started, Jack, that'd be great. It's going to take me just a second to, let's see, I need to close the other one. And then I'll bring up. Okay, so you're the Marrera group there, is that right?
Yep, that's right.
Now let's see here. There we go. Let's see. Try this again. Apparently, PowerPoint doesn't like me today. It's I'm having to restart that. Do you have the if you have that PowerPoint handy, you're welcome to share it there if you have it up.
Let me see if I can open it.
Okay, let me let's see. We'll see you can get it up. Let's see. Yeah, I think my system has started choking on all the big presentations today, so.
I'm trying to share my screen, if that helps. Hold on.
Let me see if I can share it real fast.
Okay,
I have the
good.
presentation up. I'm just gonna see if.
Okay.
You guys see this slideshow?
Yes.
All right, so are we good?
You're good to go.
All right. Sorry for the technical difficulties there. My name is Jack Barland. I'm a junior at the University of Kansas. I was part of the NASA Academy this past summer with Liz at the Langley Research Center. We kind of had, we had 17 or 18 came from all across the country to help solve the problem of fighting wildfires. And so we kind of did two groups. One of the groups was focused on kind of like a communications aspect of the process. And then the team that I was a part of, we were responsible for solving a problem that another organization within NASA was trying to solve. We kind of hopped on board with them and gave them some support, which was delivering, in our case, or in this case, I guess, drinkable water to firefighters on the front lines. And so we were tasked with finding a way to deliver our cubetainer of 2.5 gallons of water to the front lines while the initial attack was starting and the effort to contain whatever wildfire would take place. So that is going to be the focus of this presentation. I'm just going to present basically what we did. It shouldn't take very long, so we can all get out of here. So let's see. So this is basically just kind of overlaying the mission concept. So we had, like I said, a 2.5 gallon cubetainer full of water. It's basically just like it's like a water bladder inside of a cardboard box. And so that was what we were tasked with transporting. We ended up deciding to go with drones, because who doesn't like drones? And so we decided to create a package delivery system that would hook onto the bottom of an Alta X, and we would deliver the supplies that way. So this figure to the right, just, yeah.
Why don't you let me take over the presentation here, just to get it into presenter mode. And I don't see your slides advancing, so let me just tell me which. Yeah, I can do this real quick. And Just let me know which slide I need to be on. Here's the title slide. Mission
It
concept.
should be the title. Yeah, right there. That's where I was at.
Okay. I'll go ahead and advance for you.
Okay, sorry about that. So let's see, mission concept slide. So next slide.
There we go.
There we go. Okay, so let's see, where was I? So this figure on the right is basically just, you know, what the test look like. It was kind of basically the stages of the UAS during the mission. So obviously there was climbing and taxiing throughout to get to the drop site where we were going to drop the water at. And it basically just kind of shows the change in altitude over voltage. And voltage was kind of basically like our fuel. We only had so much of it to use for, you know, our power system. So it obviously shows that, you know, during higher rates of climb, you're using more voltage than if you were like hovering. And so that just kind of gives the overall, you know, lays the groundwork for the scope of the project. Next slide. So this slide kind of basically sets up more of the scenario. So in the picture to the right, the U that's within that dotted line, that's kind of the UAS drop site like base. So that's where the cubitainers will be loaded into our prototype and flown to where they need to be dropped at, near the fire line, which is that rectangle that's up in the top. And so those dotted lines are just kind of where we thought like all cleared space would need to be so that we could operate safely within our means of deployment. For this project, we normally just use visual line of sight operations. We didn't really go into extended visual line of sight or beyond visual line of sight, but that is currently being worked on. Next slide. All right. So this is kind of more in depth of the scenario. So it was kind of broken up into 4 stages. So you got T0 where the fire starts. That is just kind of, you know, the start of the fire. It starts to grow. And then you get to T1 where, you know, you have winds kind of blowing the fire in different directions. And that is kind of where you start to get UAS, you know, visual line of sight operations, start to help the firefighters who are starting to get to the scene, help fight the fire. So T1 to T2 is kind of where this project operates. In T2, you can see there, it's like a little tiny green dot by the fire. That's kind of where the UAS drop site is. And so that's where all of our supplies will be transported to. And then T3 is after, you know, the containment effort has been going on for a while. The sites are kind of being around where the firefighters need their supplies the most. And there are obviously other UAS operations going on to help fight the wildfire. Next slide. So this is kind of where the bulk of the presentation's at, this slide, and I think the next 2 or 3. But basically we had kind of a crawl, walk, run approach with CAL FIRE and the Forest Service. So the focus of this presentation is level 1. That was basically the payload delivery and our prototype design. So that's what I'm going to be talking most about. But the other 3 levels, they are in the works, and Robert McSwain, who was kind of our leader along with Liz, he's kind of heading those other 3 levels of the approach. So his email is down there if you guys want to ask him questions about the other 3 levels. So I'm going to talk a little bit about this image to the right. This is our prototype. It basically, the idea was to hold the cubitainer from the bottom with like some stability through the side so it's not shaking around and throwing off the stability of the Alta X. And so those blue paddles on the bottom are kind of what they would collapse and open up, and the cubitainer would fall out when we landed. There was a little switch on the controller for the pilot. That was kind of where we tested, was just like visual line of sight, and you know, the pilot could see everything that was going on. But they would flip a switch and the cubitainer would deploy. and we would take off and the container would be left behind. And then obviously the Alta-X would fly back to where it got the container from, where the mission started. And there would be crew to help load up another container. But yeah, so we used an aluminum frame. All the blue parts that you see are 3D printed. We used onyx filament, courtesy of the makerspace that we were allowed to use, that's on center at Langley, which was really cool. And then we also have a Pixhawk. It's that black box that's up on the top. That was basically what was kind of communicating with, would communicate with the Alta-X and the pilot on, like, okay, we're going to drop the box now. We're closed. We're going to fly away. So that just kind of gives some more depth to the design. Next slide, please. Thank you. So this is kind of the final prototype that we had. It's a little different than the initial prototype we were working on. The initial prototype had, like, the box was kind of suspended a little bit. And we found that it wouldn't deploy because there was on these hinges, these black, hinges down here, there's a pin in there, and we would flip the switch on the controller, and it would pull the pin, both pins on each side, and it would fall out. Too strong for, like, the pins to be pulled, so we kind of had to lower it to the ground. So the container kind of flies in and then sits on the ground, and then the package is released and we fly away. But we didn't really have any special tools. Nothing super high tech was at our disposal. It's got a remote unload, and we basically did this in 6 weeks. The full internship was, like, I think 10 weeks, but we spent the first few weeks trying to figure out what we were going to do, kind of, what problem we were going to solve. So with the time remaining, this is what we came up with, and I was really proud of the team for how far they came. But let's go on to the next slide. I think there's a little bit more. Yeah, so this is basically the deployment process. So I'm going to start on the top left and, like, kind of go down each row. So that first box is basically you have the landing gear of the prototype kind of on the ground, and then the second box is you have some crew who are at the UAS drop site. They load the container, and then you take off and you fly to the delivery site, and then you land at the delivery site, and then from there the pilot would flip the switch on the controller to open up the paddles on the bottom to release the container, and then we would fly away. The package would be left behind, and then we would return to where all the other base operations were going, so that we could then load another container if needed, and then, kind of keep ferrying the supplies back and forth. The idea was to have a few of these package delivery systems going at one time, so it's always like a continuous means of getting supplies to the firefighters. But that is the deployment process. So next slide. And then this is basically some of the performance metrics that we had from testing. So as you can see, obviously, as your gross takeoff weight gets higher, you use more amperage, so you have shorter flight time. I think we didn't fly longer than like 8 or 9 minutes, just, to be conservative with the batteries that we had with us. But the hope is that we would have enough batteries, enough supplies at the site to kind of go as long as we need to. So that was the goal. We also never flew above 20 knots. I don't think we were allowed to fly above 20 knots at a certain range that was on center where we tested. So those were just kind of some trends that we saw from the performance metrics. Yeah, other than that, all those other numbers are just kind of numbers. Next slide. So I don't know if this video is going to play, but if it does, all right, it looks like it's going to play, but it's like really grainy. But basically, this was our test at the certain range that we did. It was like the last day of our internship. it was kind of our last hurrah to, you know, make sure the thing worked. So here you can see the drone is taking off. There were a few moments in time where we thought it was actually going to tip over, and we didn't want that during our preliminary testing. So we kind of put those little elf shoes on the bottom. They're like those white horns on the legs, just so, you know, it wouldn't, as it was kind of gliding around there at the beginning, it wouldn't tip over and, you know, break the drone that we had. But once we took off, we kind of tested the control of the drone, took it to about 150 feet, 200 feet, and then just kind of flew it around a little bit. The pilot, Brian Duvall, made sure that, you know, he felt comfortable flying the Alta X, that everything was checking out. So we flew around a little bit, just to make sure, you know, it wasn't gonna be unstable during flight. And then we came back down to land and released the package, and then took off again, and, you know, just kind of landed off to the side. And it was, you know, it proved that, you know, our design worked. We all put in over the summer, really paid off, and I think it gave a good, like, starting point to really solve this problem, because we obviously couldn't solve the problem in 6 weeks. It's a bigger problem than that, but I think we gave a good attempt as kind of like the groundwork to go off of. See if it's going to take off and leave the package behind here.
There it goes.
Yeah.
Cool.
So the drop was successful, and then we just kind of landed off to the side and called it a day. That's probably the rest of it. You can go ahead and hit the next slide, I think. Yeah, so that was basically the project that I got to work on over this past summer. That's the rest of the team. They couldn't be here today. They all had class. Some of them actually got jobs at NASA after the internship, which is really cool. But I just want to give us thanks to them. Thanks to Liz, you know, for giving us the opportunity to work over the summer. And then obviously both Brian's from Robert's team, they were really helpful. They gave us a lot of their time and a lot of, you know, expertise and tips to help make sure the project. But yeah, that was my presentation. Thanks for listening.
Well, thanks very much, Jack, and thanks to Liz too for bringing this to our attention. It's always nice to see some bright young folks going out there and doing some really creative things. So so with that, I think just in the interest of time, we're pretty far behind today, thanks to a few glitches. And thanks, Jack. Let me bring up the next presentation here. Steve Pollard. And let's see, let me share my screen. And this is the last presentation of the day. So thanks for bearing with us here. And let's go to. And one more step here.
Com check, Everett?
Yeah, we can hear you fine.
Okay, great.
So you got 15 minutes, and I'll come back online here in about 13 minutes, so you know you have 2 minutes left, and I'll advance your slides for you.
Great. Thanks, Everett, for the last minute opportunity to squeak in and bat cleanup here. For everybody, I'm Steve Pollard from Trident Sensing in Ogden, Utah. And we're about a half mile south on the flight line from the whole Forest Service NIROPS operation, just to give you an idea of where we are. I'm going to talk about 2 SBIRs. John Green did a good shout out for the SBIR process. I'll throw one more thing on top of that, and that's I like to think of the phase 1 as a concept demonstration. Ideally, you get it beyond a white paper study to something that's starting to something that reduces the risk quite a bit. And you'll see in both of these phase 1s we're briefing, we get all the way to a flight demonstration. And then phase 2 is the full prototype where you actually go out and build a fully functioning system. So I'm going to talk about our USDA phase 2 TAC fires. SPIR, this is a tactical fire mapping sensor that we successfully made it through the phase 1 gauntlet and have been awarded the phase 2 part of it. And then a just awarded NASA phase 1 that we're working on right now. So once you advance it 2 slides, Everett, just trying to keep it down, go past the agenda. So TAC fires is we did the concept demonstration in phase 1. It was 9 months last year, where we took a bunch of emerging small components, packaged it together in an innovative way, and basically built a very small strap down sensor that can be mounted on the bottom of virtually any aircraft. No moving parts. The idea is to fill in all the gaps of those strategic sensors that are flying out there, get it to a price point that we can put it on everything, and also reduce the airworthiness requirements of larger sensors like a full FLIR ball. Next slide. So TAC fires will fit on everything you see, from the small UAS all the way up to the very large tankers. We want to make everybody who's flying out there a node, not just have strategic sensors flying up in orbit or on dedicated mission platforms. Next slide. To do this, if you're going to have hundreds of aircraft flying out there, you need to combine the data in innovative ways. So we're registering, going straight to map product, no images. Images are big, they're tough to move around. So we're going straight to map product on, we selected a 1/3 arcsec USGS digital elevation model. That's roughly a 10-meter pixel of the Earth. We're putting it into time slices, so you animate the fire. It's not a single pass at night that gives you a static image. We want everybody contributing to a dynamic image. And we're weighting the different sensors and platforms out there based on their capability. And the idea is to express the best, and but not throw anything away. So you kind of see up there, even the various platforms in space will have the lowest resolution, but at times they're the only ones looking at the fire. So you want to make sure you include them. And I'll give a little bit of a shout out to Tim Ball, because I'm reading my notes here, said we need to go to shared data. So this is a kind of a step in that direction, but I think looking at all the things that are going on out there, that we probably need a working group to figure out how to do this so that everybody can participate. And it's not just TAC fires, it's everybody who has something flying over is contributing to a common picture in a multi-user, multi-platform environment. Next slide. So in phase 1, we actually went out to the field with targets from the NIFC, flew in mountainous terrain and in level terrain. Next slide. This is just an example. We were able to prove in phase 1 with a concept demonstrator that we could get to 6 to 10% subpixel detection with a single long wave infrared band, and roughly 10-meter geolocation accuracy. And we think with better timing and new INS, we'll go to about 5 meters in phase 2 with the full prototype. Next slide. We didn't get the videos in this. This is a last-minute add-on, but go to the next slide. This example here on the left is showing you we had 3 cameras on this concept demonstrator, all strapped down. The red one on the left there is nadir. The blue one is looking off in the left oblique, and we put a narrow field of view in the center of the overlap there, so we get 3 overlapping sensors. And we go direct to map product, which shows you on the right side. And what's real interesting about this is, you know, hundreds of megabytes of data can be compressed down to just a little bit of skinny map data, making it suitable for pushing across even narrow bandwidth satellite links or line of sight links. We don't need a big broadband link in order to push the data around. Next one. That's a video, 4 hours. It was going to show the animation of the fire, the time-based aspect. We'll go to the next one. So phase one, which finished up in February, demonstrated the sensor had suitable sensitivity, geolocation accuracy. We could image fire all the way up to 10,000 feet. So that's starting to tickle where 10,000 AGL. So that's tickling where the NIROPS aircraft are flying. So you can do some of that mission. We demonstrated mapping and maneuvering. So we want to make sure that we could, in this tactical thing where you're putting it on a tanker or a lead plane or an aerial supervision aircraft, doing various maneuvering, that we could fly this as a parasitic mission and they didn't have to do special maneuvers for it. Also with the single band camera, we didn't pick up on any significant sun blooming, reflection and such. Next one. So we were picked up for phase two, which means going to a full prototype. So we'll be outfitting with approximately 8 cameras, going to real-time processing. We're going to use a Iridium Certus for beyond line of sight map transmission. That's a 88 kilobits, actually about 20 kilobits upload. So we'll verify that we can push it across that pretty narrow pipe. Central map serving. So if you have hundreds of aircraft flying, you got to centralize where you're putting all those images together, all the maps, contributed maps. Better geolocation, we talked about that. And then the big thing, one of the areas for collaborating is the priorities for different product. The idea is to have a server, you'd be able to subscribe to various map formats to overlay over your own common operating picture. We're not trying to develop a new common operating picture. Some areas for collaboration here. Combining time-based with predictive models. There was a whole bunch of discussion about that, especially today. I noticed Jessica Black in her Wi-Fi project was doing a lot there. So we'd love to take fairly rapid updates out of the this mapping and then show that feeding into a predictive model. And that way you don't have to predict too far into the future where you start getting less confidence in what's going to happen. Piggybacking other sensors. So once you have this sensor flying, think of it like a low Earth, really low Earth orbit satellite where you can put other things on it that might be of interest to this community. Firefighting data capture and effectiveness. So if you have if you know where your retardant lines are going, coverage levels, and there are a lot of people doing work on fuel loads, you could probably start to back out firefighting effectiveness and maybe make the whole aerial firefighting process more effective. I'll go straight to the bottom one, pilot input. We're looking hard at what out of this, what could be used in the cockpit to make that job easier. There's a lot of, aerial supervision's tough. There's a lot of smoke. They can't see very far in many cases, and how much of this could be piped back up into the cockpit. So we're looking for input there. Next one. I think I've got about 2 minutes, so I'm going to go really fast here. We also are in a phase one right now with NASA. We bid under the Unmanned Traffic Management Initiative. And we kind of went bold and said, what would it take to actually do aerial supervision from the ground to extend the aerial firefight to nighttime operations using unmanned tankers? So it didn't include the unmanned tanker part, but some of the technologies that would be required to control that. So it's being geared towards something like 1,000-gallon aerial delivery. The H2 Aero guys with the 3,000-gallon capability, that would fit right in the heart of the envelope here. But we're leveraging the near real-time fire mapping out of TAC fires, and then we're building web-based tools to do replicate a lot of what happens in the aerial supervision module that's flying overhead the fire. So all the airspace management, all the way to retardant delivery, and looking at what avionics package is required to do that. one more slide, and I think right about at the end here, Everett. So for phase one, we're actually going out and demonstrating this in a light twin. Has similar performance to a 1,000-gallon unmanned air tanker or seat. We're going to be flying 3D profiles. So this is geared towards entering the fire traffic area and flying a 3D trajectory that was uploaded from the ground from the aerial supervisor all the way to wind-corrected retardant delivery. And then we'll be using our phase one TAC fire sensor to do real-time map updates coming out of that. Tasking via Iridium Certus, and we're headed down to Arizona, probably Sholo, in 2 weeks to go and do the concept demonstration kind of capstone flight. We're looking for an RX burn, but weather hasn't been helping there. So we may be working off of a campfire or pre-recorded imagery from last year from the Morgan Tank Barn. So, I don't know how much more time I have.
We're running kind of behind, so we should probably wrap up. I think you're probably about out of your 15 minutes there.
Yeah. So lots of areas to collaborate, especially in the predictive fire tools. So to make this work, you have to replicate everything that the aerial supervision module does daytime with eyeballs in the air. So knowing where the fuels are, looking at the wind and the weather conditions, where the fire is progressing. So a lot of what we talked about today could be tied in to help give that situational awareness for nighttime aerial supervision from the ground. So that's it.
Well, thank you, Steve. And I do hope you get your controlled burn, because I think that makes a big difference if you can, if they can pull that off. And I know that it's that can be tough getting those things lined up, but
yeah, it's the moisture content from the monsoon season down south has made it tough, and we're in full winter up here in Utah, so we'll probably end up with a fire of opportunity.
Right. Well, thanks so much, and thanks for coming in at the on short notice like that. I guess at this point, we're pretty far over our scheduled time, but I wanted to see if my co-chairs would turn on their cameras. I don't know if let's see, there's Mike. Is Birgit still with us? She may have dropped off. Let's see. But Vince or Mike, do you have any thoughts you'd like to share as we wrap up here? I kind of ran out of gas. I don't know whether it was because of some of the technical issues we had here, but yeah, I think we had some really great presentations today. There was a lot of great exchange going on in the chat. And so that's one of the nice things that comes out of this meeting, is that there's engagement that goes on between folks. And so Vince, Mike, any thoughts?
Mike, go ahead, and then I'll follow you up.
Okay. I mean, the thing that really comes to mind for me is seeing all these incredible advancements is interoperability. So there's not only user readiness for the new technology or new data set that you're trying to bring into the fold, but there's interoperability readiness. Is your data set ready to complement and integrate with existing tools? Because there is no single source of data or technology that will address all of the problems in this space. It really must be integrated, and everybody knows that, of course. But that's a tough one. Even from like the NOAA satellite perspective, we focus a lot on user readiness, but not a lot on how our satellite data is going to integrate with all of the other sources of data, because it's a big effort. So that's a big challenge. I'll leave it at that.
Yeah, I think that's a consistent challenge, is the interoperability. And, you just look at things like radios, that's been a huge challenge on disaster support incidents for years. And that's something that they're still wrestling with. And but just, the data, having the data readily available. It was Stephen his name escapes me at the moment. And Stephen, yesterday our kickoff speaker mentioned the data lakes, and he had the diagrams showing that, yeah, Stephen Nelson, thank you. He mentioned how we need to get things more collaborative in the data environment, the IT environment, so that things can be more readily available to folks. And, so it's not just the remote sensing piece. There's a lot of different pieces. It's a pipeline. You have to have some way to collect data through sensors, a place to process the data, a place to put the data where it can be used, and then produce products that can be used by folks on the ground. And with fire and disaster support, that pipeline has to be very efficient and very short to reduce the latency to as much as possible. There's Birgit. Hi, Birgit. So yeah, this is everything working together, moving in a positive direction here. And so Birgit, did you have any thoughts? Oh, you're having technical difficulties. This seems to be the day for it. Yesterday things went so smoothly, but let's see, Dave Jones said, thanks, co-chairs, for an excellent TIFRSAC. Interoperability can also benefit from partners with a vision for interoperability and not tied to one project, mission, agency, or mission. A good reason to think about a TIFRSAC testbed. So Dave, we're going to take that to heart and carry that forward as one of the action items from this meeting, is to look into the notion of having some sort of testbed, I guess. So
do you have any comments, or?
I think she has some audio issues, so.
Okay. Couple things that I noted. One of the, especially today, what really stuck out to me was some of the discussion we had right before the break with Tim Chavez, Phil Saleg, and I forget who the third person was.
Josh Wilkins.
Yeah. That really, really ignited in my mind our original concept of the TIFRSAC, was to combine the technology people such as us in the Earth observation and geospatial technology field with the firefighting management community on the ground, to listen to them, to hear what they had to say about what their needs were. And I just thought it was great having those guys, and I hope they continue to be part of our TIFRSAC, because that's the key component. Otherwise, we're building tools and capabilities and advancing science and improving our technology modes without really having a focus of what the intended user really wants. So as I said, and as Everett has said previously, our TIFRSAC was originally designed to combine the eggheads from NASA and industry and universities and other federal agencies, and bring them together with the really field managers or fire managers on the ground, the technical fire management community, and to really listen to what their needs were. So I encourage the members of the Forest Service, CAL FIRE, and those agencies and entities to stay involved in our community, to really give us a direction forward on what we really need to be doing to make your jobs easier and better. And for those of us in the technology realm, especially from industry and university community, academia, really look at the, and maybe ever we share this, the documents again, really look at the matrix that was developed out a few years ago by Evans Cole and has been added onto, to really see what the community has said their needs were. That'll give a lot of direction to those that are seeking new funding opportunities from our various agencies through solicitations, and it'll give them a head start on what the community really wants to or needs in the maturation of Earth observation capabilities and geospatial technology. Additionally, what might be of interest to people is go back and look at the documents that were generated from the NASA stakeholders meetings, and I think we've shared websites on those as well, where NASA's purpose was in those workshops was to listen, not talk, but to listen to the community and hear what they had to say about what their needs were. So if we re-examine those between now and the spring meeting, I think we'll have a really good handle on creating more involved partnerships with our partners in the fire management community. And that'll also help to bring in some of the people from industry and the university realm into a clearer picture of what they can help to mature out very rapidly into new technology and fusion elements for practical use with our partner entities. As you saw, there was a number of new solicitations out on the street. You know, we posted some of those. So be aware of those coming out. There will be some coming out from NASA, as we had mentioned in Mike Falkowski's presentation yesterday morning. So stay tuned for those announcements coming out for the wildfire solicitation elements. I think Mike also mentioned a few elements, solicitations that are coming out. And additionally, I might remind, I don't know if the person is still on the line, who mentioned the, in the chat yesterday, I believe, mentioned the position opening at JPL for a fire scientist. And then yesterday we also mentioned, Mike Falkowski and team mentioned that NASA has a position for a fire remote sensing scientist as well at NASA Ames. So those are two positions that some of you students may be interested in, or some of our partners in other federal agencies may be interested in applying for those positions. So two new positions within NASA, and I'm sure Mike probably has others as well within NOAA, and maybe Birgit as well. So stay tuned, keep involved in the community, everybody, and I'll give a little heads up about in the spring, when we have our spring TIFRSAC meeting, we will hopefully, keeping our fingers crossed, have it as a blended meeting of both virtual and in person. We'd like to have it at NASA Ames Research Center. That'll probably be in the April-May timeframe, depending on schedule and jockeying around other meetings that might be interference with things. And then the holidays that might interfere, such as Easter and the like. But we look forward to seeing you in the spring, either virtually or in person. And send us ideas and share content with us. Everett has mentioned he'll bring up and present all of the PowerPoint presentations as PDFs. If you do not want your presentation shared with the community at this point, just let us know and we'll ensure that they're not. Everett, I'll let you speak further to that end.
Yeah, and I have a couple things. I actually wanted to read Birgit's comments here since she's having the audio, because I thought her comments were very insightful. I'm struck by the steady advancement of ideas from conception to practice over the 10 years or so I've been participating in this. That has brought to light again. That was brought to light again during the last 2 days of talks. I hope the trend will continue, and we'll be looking forward to the next round of talks in the spring, hoping we continue with the momentum that Everett and Vince have generated with the TIFRSAC community of practice. And thanks for that, Birgit. I also wanted to, Marva must have been reading my mind, because I was just looking up a comment that she had made earlier, and she mentioned to me yesterday that they're updating the requirements matrix, and there's no timetable on that, but they're working on that. So I'm really glad to see that, because I think that the first round of the requirements matrix was really well done by Evans Quo, and but there's some things that we can do to tweak that that can make it more useful. So Marva says here, the interagency wildfire ops tools and technology and aviation are reworking the requirements matrix prepared earlier by Evans Quo, likely available in the spring. So thanks for that, Marva. Couple other comments here. It's getting a little bit late, and I kind of have a hard stop here at the bottom of the hour, but I did want to thank everyone that stayed on the call today, all of our presenters. We had some tremendous presentations this time around, really fascinating and thought-provoking. So, you know, I'm really happy. This is the high point of the year for me, having these meetings, the spring and the fall meetings, and they've been kind of the highlight of my career to be able to participate in this kind of a community of practice. So I thank all of you for contributing to this. And any final thoughts before I push the leave button here at the bottom of the hour here?
Well, we'll see everybody in the spring, hopefully in person and online. We'll make it a blended meeting or a hybrid meeting, I guess, if we can. And we look forward to being able to meet people in person and share a beer, soft drink, or a glass of wine, and do the hallway conversations, which are really where the work gets done and the collaborations are developed.
Right.
Can we allow Mike the time to put in the links that were just requested? Maybe you could get off and then we'll just all close out.
Yeah, well, I can leave this running for sure.
Mike, I don't know if you see that, but there are requests.
Yeah, I did. Yeah, I'm tracking that down now.
Okay, sure. All right. So thank you, everybody. You guys did an amazing job, always, and better even this year.
Well, thanks for being on, Amber. It's really good to have you participating in the meeting. And so, yeah, you add a lot to the meeting. I appreciate that.
We miss you, Amber.
I miss you guys too. I'm not sure who said that, but
that sounded like Ed Freeborn.
We miss you, but our aim is getting better.
That's a lot.
That's
a lot
from my
about
big brother. I recognize that voice anywhere.
All right. Well, I'm gonna
Thanks.
I'm gonna leave the meeting running here, but I need to peel off. So folks can stay on as long as there's the links from Mike. And I will go back and capture a lot of the information in the chat so that we can share that and make sure that everyone's questions and comments have been fully answered.
Great. Thanks again, Everett, and thanks for putting together the summation with all the presentations. And we'll get that information out to everybody via an email link in the next week or so. Thank you.
Sounds good. Thanks, Mike. Thanks, Birgit, and thanks, Vince.
Thank you.
Thank you. Bye.